Hello everyone. Let's do take 2 of the week 15 homework. Yeah. Um, got a little bit interrupted, but I'm back. So yeah, here's your homework. It starts with the first problem is about Kirby who hits a ball. It's another baseball problem. And you're going to want to take out your calculator. Most of what we do is going to happen in here. You're going to want to hit mode right away. Make sure you're in degree mode. Make sure you're in parametric mode. That's where you're going to want to be. And I think I want a thin graph. I don't care about the dots anymore. I've decided I'd rather have the thin than the dots. At least on this calculator, the newer one that has that option. That's what I'm going for. So okay, we're ready to go. But what are we going to do? Let's read the problem. It says Kirby hits a ball when it is 4 feet above the ground. So if you're planning out what's going on, then it sounds like we just learned that the initial height of the ball is 4 feet. We could label that 0, 4. That's the initial height. We also can read that he hits the ball with an initial velocity of 120, and that the ball leaves the bat at a 30-degree angle. So what that's doing is defining a vector, a force vector acting on the ball. So if we establish this horizontal line, then we know this angle is 30 degrees. The initial velocity is like the magnitude of the vector. It's 120. So there you go. There's our force vector. Now the actual path of the ball, it'll follow that vector at first, but soon enough, gravity is going to start to try to pull that vector back down, and you're going to end up with that parabolic flight. Okay, so that's what's happening. So now, if we wanted to actually model this, then we would need to use our equations. We know that x of t is the initial velocity, which is the 120, multiplied by the cosine of our angle, which is 30, multiplied by t, which is time in seconds. The x equation is simple. The y equation is the same as the x equation, just with sign. But in the y direction, you've also got gravity, which would affect your height, so you've got to incorporate that. So minus 16t squared. But you've also got that little nudge up, the initial height. You've got to add on those extra 4 feet. But these two equations here are the set of parametric equations that will model our parabolic projectile motion. Hope you like words that begin with P. Okay, so let's get those into our calculator then. Bong, there's our calculator. Y equals, you gotta type it in. 120 cosine 30. Close those parentheses, then type T. 120 sine 30. Close, type T. Minus 16t squared plus an extra 4. Okay, awesome. Now we hit graph, and no, that's bad. This is the part where if I'm you, I pause the video and I mess around with the window myself and I try to make it look good. Take that as a little challenge to yourself, okay? Okay, I'm back. Here's what you should have done. The time could be almost anything, really. You definitely want to start time at 0. And 10 seconds is typically more than you need, and 10 seconds is fine. Set your scale to 0.1. That's typically what you want to do, and that's fine. In the x direction, the wall is 350 feet away, so we know we got to go at least that far. I'm going to go out to 500. That's supposed to be my min. My bad. So I'm going to go negative 50 to 500 because I've decided I do want to see the y-axis a little more clearly. Then the y min, I think I want to go down to 20 up to a maximum height of 100. Is that high enough? I'm not sure. Let's hit graph and see what we see. Boom. That looks great. Here's what I don't love. The y-axis looks all weird. Why is it all thick like that? Well, the y-axis is trying to plot 120 little tick marks. That's maybe too many. maybe we should have the scale be 10. Suddenly now when you hit graph, it's only showing a few of those little tick marks, and they're much more useful. It's showing you 10-foot increments at a time. Same thing's happening on the x-axis. If you're wondering where that 350-foot wall, or the 350-foot away wall that's 30 feet high is, you have no idea. You have no benchmarks to look at. So, or mile markers. Why don't we just have our scale go by 100? And then at least we know what 100 feet looks like. Suddenly now, I have a much more useful looking graph. I see there's 100, 200. I see the maximum height occurs at about almost exactly 200. I see that my maximum height, I can expect it to be 10, 20, 30, 40, 50, 60, about 60. I can see that I hit the ground after about 400. This is better. It's obviously better. So I've always kind of glossed over on the X scale, Y scale part, but no, I think we should really think about including them. So anyway, here's a wonderful looking graph. If you want another secret pro tip, I'm going to go down to this magenta one. Oh, I did want green. Okay, I'm going to do it on the green one. We could actually render the wall if you wanted to. Where is it? 350 feet away? I guess my X equation should be 350 then, right? My Y equation, I want to plot a vertical line that goes as high as 30. Now, we set T to go all the way up to 10, didn't we? So what if I just multiplied 3 by 10? Then I'd be multiplying all the numbers from 0 to 10 by 3. That would give me all the numbers between 0 and 30. That's going to plot a vertical line. Okay, ready for some movie magic? Boom. There's our wall. So now, you guys can tell just by looking. Is this ball going to go over the fence? Nope. I can see I'm at a height of 30. Are you guys going to know how to do that? No. Is this how you guys should do the problem anyway? No. I just want to really show you, a good looking picture that really explains what's happening here. You can see this is the path of the ball. It would hit the fence high up on the fence and it would bounce back into play. It's not going to be a home run. Let's now actually do the math to figure out why that is. So what math do we do? Well, let's go back to the flip chart. So we've got that fence that I just told you was 350 feet out. So we're concerned with the point on the graph. That's 350 feet out. So for every point on the graph of parametrically defined functions, there's a t that you should know, and then there's an x and a y coordinate. So in every situation, you know one of those three things. In the case of this wall that's 350 feet out, it's the 350 that we know. We know the value of x. We'd like to know the value of y, because if the value of y is greater than 30, then we know we're going to clear that 30-foot fence. If the function is greater than 30, then our fence will go doop, and it'll only come about this high. 30 will be, the ball will be higher, it'll go over, it'll be a home run. But we already saw in the calculator that our height is going to be something more like, 27 feet or something, which means our wall actually comes up higher than the ball. And our 30-foot fence is higher than the height of our ball, so it's not going to be a home run. But that's what's happening here. So how do you get the y value? Well, you have to find t. You need to know t if you want to find x, and you need to know t if you want to find y. So if you know x, you got to find t, then you use t to find the y. And the reverse is true too. If you knew y and you wanted x, you'd have to use y to find the t, then you use the t to find the x. So there. So how do I do it? Well, it's not that hard. You go grab your x equation. And since x of t is 120 times the cosine of 30 times t, we know that we want the distance traveled horizontally to be 350. So to solve for t, you're just going to divide by this coefficient. So you'll go 350 divided by 120 cosine 30. And we can do that in the calculator. So we go 350 divided by 120 cosine 30, hit enter, get 2.525, which seems completely plausible, but we know it's wrong. If we were in class right now, I'd say, why are we wrong? And maybe somebody would answer me, but probably nobody would. I'll give you the benefit of the doubt. Somebody would have answered me. You guys are remembering we have to actually use parentheses, right? When we divide, you have to divide by that whole entire product, so you better use parentheses. And then do your 120 cosine 30. We are going to get a completely different value now. So be super careful. Be super careful, okay? Because this math is really easy. It'd be a shame if you screwed it up just because you didn't use parentheses. So now we've got our real time. I'm going to store that time as... I'm not going to store it as t, because t gets overwritten sometimes. I'm going to store it as a. But I've got it. So now I can pretty quickly take that t value and plug it into my y equation. And I can do that in the calculator too, in two ways. I can go second calc and choose value. And then you can enter a t value. So alpha a is my t value. And it'll actually show on the graph that when x is 350, the time is 3.367, and the height is only 24. We were trying to go over a 30-foot fence, so we know it's not happening. Now the better way to do this, though, is go into table setup and set your table up to allow you to ask for the independent variable values. That's the t's. So now instead of an auto-generated list of t values and stuff, we can ask for our own t's, the only one we care about, and it'll give us our answers. So we can see that our height at the time is 24.591. So let's take that information now and address the problem. This question said, does the ball clear the fence? If you want full credit, you're going to write me a sentence where you say, when x equals 350, t equals, I already forget, 3 point blah blah blah, 3.368. And at that time, y equals 24.591, which is less than 30 feet, so the ball will not go over. That's what I want to see. So if you're trying to get full credit, and I'm sure you are, you'll mention to me that you know that the given x value was 350. At that time, that generates a t value of 3.368. That t value corresponds with a y value of 24.519. And you'll compare that with the 30-foot height of the wall. You got to make mention of all those things. There's no work you have to do. So the trade-off is you got to actually write me a well-reasoned sentence. Well-reasoned. And there, you'll get full credit. The ball does not go over. If you just say the ball does not go over, you're not getting credit. I need to see these numbers. Okay, great. There's a part B, right? So if so, by how much does it clear the fence? Well, it doesn't clear the fence. If not, could the ball be cut? This question is, is a little weird. It kind of threw me. But this is a 30-foot fence. So if I'm a person, I'm a 6-foot tall person, almost. You think I can catch a ball that's at a height of 24 feet? Yeah, probably not. I can reach up real high, I can jump as high as I want, but no, I won't be able to catch it. Not before it hits the ground. Maybe it'll hit the wall and bounce, and I can catch it on the bounce, but the question means, can you just catch it directly before it hits anything else? The answer is no. For a 6-foot baseball player who's in reasonable shape, can reach his arm above his head, he's got a glove on his hand, he can jump. What do you think, 10 feet, maybe? Maybe if the ball was lower than 10 feet than this left fielder, center fielder, whatever he is, maybe he could jump and catch it, but no. I don't love part B. I don't really care how you answer part B. But I would say B. No. The ball is too high. 10 feet is a reasonable max Anything over 10 feet, you're not going to have a shot at. Okay, great. We're done. Moving on. We're not done. There's a new question about Kirby that says, hey, in problem number 1, it was a nice calm day. But in problem number 2, we're saying that at the exact moment, or shortly, a millisecond after Kirby hits the ball and the ball leaves his bat, there's a split-second gust of wind that imparts an extra and second force to the ball. And suddenly, I love this problem because guess what? Now we're marrying our unit on projectile motion with our unit on vectors. Suddenly, that vector that was affecting the ball before, which was what? A vector with a magnitude of 120 that acted on a 30-degree angle. It is now having added to it a second wind vector. And it says, assume the wind acts in the horizontal direction with the ball. So that means there's a vector up here. I'm going to put it right at the tip of the other vector. Its magnitude is only 5, and it acts exactly horizontally. So that means we're doing a brand new question with a brand new vector affecting the ball. It certainly looks to me like our magnitude will be increased, not by 5, by a little less than 5. And the angle is going to change. The angle is going to become a little bit less. So the question is, as that angle becomes less, the ball won't go as far. But we are adding on a slightly stronger force. So what's going to happen? Are we suddenly going to be able to clear the fence now? Well, we've got to come up with the component form of this vector. Now, we don't really need the component form. I lied. But if this vector is r for the resultant force, what we really need is the magnitude of r, because that will be the initial velocity. That will be the v0 in our new equation. We also need to find its direction, because that'll be, well, the direction in our new equation. So how do we find the magnitude? Well, we gotta render this thing down. We gotta get it in component form. So to do that, you're going to want to render the red vector down to its component form. Let's just call these vectors A and B, I suppose. We'll let the colors speak for us rather than the names. But this vector, this first vector, is going to just be 120 cosine 30. And the vertical components will be 120 sine 30. And I didn't mention this in the previous problem, but we know what sine and cosine of 30 are. We should know that cosine of 30 is root 3 over 2. So 120 times root 3 over 2 is going to be 60 root 3. We actually know what this thing is exactly. We don't need to mess around with decimal values. And the sine of 30 is a half, and half of 60, or half of 120 will be 60. So there's our vector A in component form. And vector B in component form, you don't have to do any math at all. You can see that the horizontal component is purely the 5. It's just fully horizontal component and no vertical component. It's 5, 0. Let's say you didn't really process that. Then you would do what? Magnitude is 5 times the cosine of, well, the angle is 0. It's going straight east. So cosine of 0 is 1, and 5 times 1 is 5. So you'd get that answer. If you did 5 times the sine of 0, well, the sine of 0 is 0, so you would get 0. So you would get these values if you used this formula, but common sense would seem to indicate that if the vector goes 5 units to the right and that's it, then its component form is 5, 0. So anyway, as you all know, since vectors are on this quiz too, you know that our resultant force, R, is literally just the sum of these. So we know our horizontal component will be 60 root 3 plus 5, whatever that is. And you know that your vertical component, well, that'll still just be 60. Okay, now that I've got those components, I can find my magnitude, I can find my direction, using the same formulas from the vector unit. So v0, our initial velocity, which is represented by the magnitude of the vector, is going to be found using our formula, r1 squared plus r2 squared. And take the square root of all that. I'm just going to do it in the calculator. So here's your calculator, so I can quit, whatever, clear. let's do the 60 root 3. Sure, let's just say enter. And then we'll add 5 to that. Enter. And then we'll go under a radical. And we'll take that answer and we'll square it. And we'll add to that 60 squared. And there it is. That's going to be my horizontal component squared plus my vertical component squared. So there's our new magnitude, 124.355. I'm going to store that as v for my initial velocity. You guys know I'm just mad about storing things in my calculator. So bam, there, it's stored. And now I can't lose it. 124.355. What is this, feet per second? But I also need my new direction because we know that that wind that's blowing us exactly east is going to kind of force our direction down a little bit. We're going to have a smaller measure. So this is where you need to recall that we had a formula for phi, which was do the inverse tangent of your R2 divided by your R1. And that phi is not usually our direction, but in quadrant 1 it is, because we've got our vector. When we find phi, phi is also our direction, theta. So we won't have to do anything to this. It'll just be good to go. Now I'm feeling really sad because I never actually saved this value. I want that 108. That 108 is our R1. That's our horizontal component. So let me just grab it and get it in. That's now my answer. So now I can do second inverse tangent of my vertical component, which was 60, divided by my horizontal component, which is the 108 from a second ago. So second answer, enter. There's our new angle. We used to be on a trajectory that was 30 degrees, but that slight easterly wind has pushed us down a bit. Now it's 28 point blah, blah, blah. I'm going to store that, because of course I am, as theta. Look, theta is available as a variable, so I'm going to use it. 28.848. So now that I've got these new values, that means we have to basically redefine our functions from problem number 1. So under the condition of that wind blowing Kirby's hit, the new equations would be x of t equal our new velocity, 124.355, times the cosine of our new angle, times time in seconds. And our new y equation would be, I really don't feel like writing it out, so I'm going to use my variables. We said v sine theta t minus 16t squared plus 4. So I can type this into my calculator now. And rather than replacing the blue, I'm going to enter it in as the red. And I can literally use the v and stuff because I've saved those values. So instead of 124, I'm just going to type v cosine. Instead of 28 point blah blah blah, I can actually just say theta, and my calculator understands. Now on the next line I can say alpha v sine theta t minus 16t squared plus an extra 4. Alright, drum roll please. Do I have the wall in? Yeah, the wall's in. So hit graph. Boom. We can see that suddenly that little gust of wind on our red trajectory, our ball suddenly does now travel further. It is a little higher when we get to 350. Is it actually clearing the fence? I'm not sure. Let's go zoom in on the action. Zoom in for. When you zoom in, you have to actually use your cursor. You want to put your cursor on the point that you want to zoom in on. Otherwise you get a crappy zoom. So blood out. Well, would you look at that? Suddenly, we do have a home run just because of that little puff of wind, that little 5 mile an hour puff of wind. What'd you say? Did you say you can't just take this graph and send me the graph and say, look, it worked? Because you won't get credit for that? Yeah, you're right. So let's take that, tuck it into the garbage, and let's do the math for real. If you want credit, then I'm going to need you to give me a t value. So we still know that x is 350. The fence hasn't moved. But using our new equation, we know that our t value is going to be 350 divided by the coefficient of t, the 124 cosine blah blah blah, which I'm still just going to say it's the v cosine theta. And all that junk is still saved in my calculator, so I can go to my calculator and just do it. So I can quit. To find our t value, we'll just do that same 350 divided by parentheses. For the love of God, children, parentheses. Alpha v cosine theta. Close, close, enter. There's your new time, 3.213. I shall store that as b. We haven't used b for anything, or have we? Alpha b. Yeah, b's nothing. Oh no, I ruined it. Okay, go get that value. Bonk. Store it as alpha b. Okay, hit enter. Second quit. I don't have to hit quit. Go to your table. Boom. And type in your new b value, which is slightly different from the old one. And notice our original blue function. Well, that's odd. Why are they giving the same heights? Oh, because it... No. What? I'm confused. Why am I confused? I don't like to be confused. Same heights, huh? That's not something I expected. But I should have? Okay, I'm going to shut up. Okay, whatever. That happened. That's fine. More importantly, take a look. When the red ball has gone the 350 feet, what's its height? 31.594. That is higher than the 30-foot wall. But look, when the blue equation had gone 350 feet, it was only at a height of 24. So ignore this blue data. This blue data is irrelevant. And ignore this red data. That data is irrelevant too. This is the thing that matters. We have proven that the new function at 350, by the way, look again at the round off error. If you see that many zeros in a row, that's round off error. It's highly unlikely that's real. So we can rest assured that's supposed to be exactly 350. And our height's 31. So again, you got to give me those values. So what's our time? 3.213. So you better reference this time. And then you better point out, you'll say x equals 350 when t equals 3.213 and y equals whatever it was, 31.594. Which is high enough to clear a 30-foot fence. And I think the follow-up question asks you, by how much does it clear? Yeah, so by how much does it clear? So just build that in. You'll say it's high enough to clear a 30-foot fence by 1.594 feet. So there, that would be the end of our question. We see that yes, it now does clear the fence. Okay. So this is a nice question. This built in some review of vectors and everything. That's great. And it's done now. So I'm gonna move on to number 3. So number 3 is about Tony and Sue. They're launching yard darts. Okay, I'm back. Okay, I'm recording again. I hit pause because I wanted to go find you guys a picture of lawn darts because I'm not sure you know what they are. Because you shouldn't know what they are because they're illegal. I think they existed when I was a kid. And, well, look at them. It's just a big, heavy piece of metal with a sharp end. It's a literal dart. And, yeah, you'd give them to your kids and they'd go out in the yard and they'd huck them as high as they can in the air. And every once in a while they'd come down and they'd hit you in the eye. Or they'd pierce your skull. So yeah, they're illegal now. But you can get these. They changed them to just look like this. So it's the same concept though. You take this thing and you throw it and you try to get it to land inside of a ring. There. Now you know what a lawn dart is. Okay? So this is all happening on the horizontal. We can sketch this out now. Give me an X and Y axis. The question says Tony throws his dart directly at the target. He releases it 3 feet above the ground, so there's your initial height, that 3. So that's H naught? No, we called it Y naught, didn't we? Either way, it's 3. Then the idea is 20 feet away is the beginning of the little hoop that you're trying to get the ball to land in, or the lawn dart to land in. So ellipse, green, maybe it's about that big. So one end is here at 20. Now where's the other end, you might be wondering? Why, it's got a radius of 18 inches. Well, inches are no good. 18 inches is 1.5 feet. But that's also a radius. So that means from the center out. So the total length of this thing is 3 feet, which means a successful lawn dart toss by Tony has to land 20 feet away or 23 feet away or somewhere in between. Okay, so we want this thing to land somewhere in between. So, like, what do we do? Well, he's throwing it with an initial velocity of 30 feet per second at a 70-degree angle. So again, measured against the horizontal, that's a pretty steep vector. We've got a 70-degree angle, 30 feet per second. I have no idea whether that's a strong throw or not, but the idea is the lawn dart's going to go up, come back down, and if it lands here, then we have a winner. If it lands too far, if it lands too short, then no winner. There are 2 ways you could attack this problem. One way significantly easier than the other, but not as good. Here's the thing. There's let me draw this as if he missed. I don't know why I did that. I can keep that drawing. Just go like this. Sorry, Tony, you lose. There's 3 things. We could consider the case that Tony lands like exactly 20 feet out. We could consider the case that Tony lands exactly 23 feet out. Or we could consider the case that Tony lands where he actually lands. So for these 3 different positions, what do we know? Well, for this position, there's 3 different things. There's time, there's X, there's Y. Do you know the time it takes for the lawn dart to get there? No. Do you know the horizontal distance traveled when it gets there? No. Do you know the height of the lawn dart when it gets there? Yes. So one approach would be, take the y equation, set it equal to 0, find the time, and then find the distance. If the distance is greater than 20 but less than 23, then you know that Tony's a winner. The other approach I'm thinking of is, let's take just the start of the little circle. And again, do you know the time it takes to get there? No. Do you know the horizontal distance traveled to get there? Yes. You know, it's 20. Now you don't know the height though. So the idea is you could use x of 20 to find the time and then figure out the height. Now remember, our model will assume that Tony's lawn dart will hit the ground and then just continue to burrow its way all the way through the earth and then all the way down to hell. Okay, not really, but you know. So what would happen then here? Wouldn't you get a negative height? If the lawn dart had already hit the ground, then you'll get a negative, right? And of course, if the thing is like this, if Tony's throw went too far, boop, then by the time you get to 20, you'll have a height that's still positive, meaning it's still in flight, okay? So that's another way we could test it. That's the easier way, but maybe slightly less sophisticated mathematically. I have my suspicions whether you care about mathematical sophistication. Doesn't really matter. Okay, what about this point? Do you know the time? No. Do you know the x-coordinate? Yes. You know it's 23. So that's the thing. If you tested 20 and got a negative height, you could conclude that Tony's shot for sure comes up light. It didn't go far enough, and it already landed. But if this was our situation, right, then when you test the 20 and you get a positive height, you still have to wonder, maybe in the next 3 feet it's going to fall and land in the circle. So now you'd have to test 23. And this time, if you had a positive height again, you would know that the thing is sailing over the target. It's not in the target at 20, it's still not in at 23, so it sails and it goes long. So my inclination is just to test for when the damn thing hits the ground. Just run one test to find when it hits the ground, okay? I don't know, do I need to do all these things? Maybe I do, maybe I will. Let's write our equations first, though. I know I need those. Initial velocity 30. Yellow. Anything but yellow. All right, 30. Cosine 70. T. That's x. Initial height is 3. Okay, great. So 30 cosine 70, we can go to our calculator, quit, clear. Let's do the easy way first. If we were trying to figure out the time when x was 20, then we would just do 20 divided by the 30 cosine 70, remember? So there's the time. I'll store that as t for time, I suppose. Let's save these equations for posterity. Nah, let's delete them. And let's delete our little guy. Our little wall. We don't need a wall anymore. So right, enter the equations. 30 cosine 70 time. Plus 3, right? Okay. Just because I'm curious. Let's go to the window. I'm going to change this to 9 seconds because of reasons. Let's go to the magenta one. And what do I want my x to be? I want my x to vary from 20 to 23. So I'll do 20 plus a third of t. That's why I made it 9. Because now 9 divided by 3 will add on the x to 3. And where do I want this to be? At a height of 0, of course. Now when I hit graph, the window. So unsatisfying. I guess that's good. Let's go -5 out to 25. We know the target's at 23, right? The y stuff would be -10 feet. How high is Tony throwing this? 30? Let's try 30. Graph. Okay, so we can see it now. By entering that second set of equations I entered, I was just rendering a horizontal line segment of length 3 that went from 20 to 23. Again, you guys will not do this. I'm doing it just so you can look and quickly see that, nope, poor Tony's coming up short. Okay, we can see that. And I just wanted you guys to be able to see that. So now what? I already calculated our t value, which means I can go into my table, delete these old ones, I guess, enter my t value, and you can oh no, I forgot. The t gets overwritten when you graph. When you hit graph, all those t values come from the t that we plugged in. We varied t from 0 to 9 by 0.1. So of course t is worth 9 right now. That's the last thing we plotted. So I better go back to the home page, and I'd better grab that number again. Oh boy. Grab that number again. And let me store it as something else this time. A. A is a nice safe place to store it. Now let's go back and enter in A. Alright, there you go. So we can see that at the time we got to 20, the height was already negative. That meant we had already hit the ground. And of course that bears out in the graph that I was showing you guys. We can see that Tony has already hit the ground. There's the little hoop. He didn't make it. So we could quit at this point and say that he missed because the negative height at the 20-foot mark implies that it already hit the ground. That's not what I would want you to do, though. So that's not what I'm going to model. So taking you guys back, what I would much rather you did, and what I think you should understand is, the better approach here is let's figure out when the lawn dart actually lands. Set the y equation equal to 0. Now this is the annoying one where you've got yourself a quadratic equation. This would be bx plus ax squared plus c equals 0. Remember the coefficients of a quadratic? The coefficient of x squared is a, coefficient of x is b, blah, blah, blah. So these numbers are your a and your b and your c. We've got to use quadratic equation to solve. We did go over this in class. I'm going over it again. So bring up your calculator, blood out. Enter negative 16 and let that be a. 30 sine 70 is the coefficient of t, so store that as b. And the initial height of 3 is our constant, that's c. So now that those three values are there, I literally just do the quadratic formula using the a, the b, and the c. So you go negative b. Now we already saw that in the plus or minus, the plus is what actually gives you a negative answer, which you don't want. So let's just do minus right away. Square root of b squared minus 4ac. And I just hit enter on that. And then divide that by 2a. Now if you don't use parentheses, you'll get it wrong. So you might just want to remember that if a is 16, then 2a is negative 32. You could just divide by the number. Or just remember to use parentheses, 2a. But our negative is going to get divided by a negative, it's going to be positive, and lo and behold, we've done it. We have found the actual time for the lawn dart to hit the ground. So we'll store that as, I've already used a, b, and c, so I shall store it as, not t, because t changes when we press graph, f for Fantagrassi. How about that? Boop, there, stored. Now I go to my table, and I enter in that value. F comes after E. There you go. Alright, so we did it. We can see now that it's showing that's supposed to be 0. Remember round off error. I don't remember if I had my whole spiel about round off error in this video yet, but that's just round off error. And we can see that when we hit the ground, we've only gone 19 feet, and to get in the ring, we had to go 20 feet, and that's not far enough. So there. That's the better way to do the problem. So I'm going to write my little summarizing sentence that way. I'm going to say, y equals 0 when t equals 1.863. At that time, the lawn dart, the super dangerous, murderous lawn dart, has only gone 19.111 feet. shy of the 20-foot target. Sad face. So that's the kind of answer I'd want to hear. You mention that you know that you're interested in a y value of 0. That means hitting the ground. You mention that you calculated the time associated with that y value, and then you mention the x value associated with that time, and then you check that against the target distance, right? So it's shy of the 20 feet target. It is not between 20 and 23. It is too small, so sad face. That's the approach I would have liked to have seen you take. If you took another approach and did the math on the 20 and the 23 and gave me the values and your reasoning was well thought out, you'd get full credit. But this is what I think the spirit of the problem was more interested in. There is one more problem. Let's do it. We're at the 45-minute mark already? Okay, whatever. Hey, it's lawn darts again. You guys didn't forget about Sue, did you? So Tony just had his shot and Tony missed. Now it is time for Sue to try. So okay, what happens? Well, Sue is using a different force and a different angle. So her trajectory will be different and governed by different equations. So she's doing 25 cosine 55 times t. Her y equation would be 25 sine 55 times t minus 16t squared. She releases from 4 feet high? Okay, so plus 4. Okay, Sue, go ahead. Let's enter them into our calculator. Y equals. I'm not going to overwrite this. We're going to leave it. So the path of Frank, what was this dude's name? Tony. Okay, Tony. So we're going to leave Tony in there, and we'll plug Sue in as this one that's going to be red. So she chose to huck the thing not quite as hard, and she chose to huck it on not quite a steep angle, or as steep of an angle. And we'll see if that rewards her. T minus. She hucks it from a little higher too, from 4. Yeah. All right, so we hit graph. And we are shocked and amazed to find that, wow, hers doesn't go as high, but it does go farther. So even though she threw it with less force, she threw it on a better angle. Tony threw his way up high, so it came down short. But she's hitting right in the sweet spot. We see that it is hitting that magenta line segment that I showed you. So how do we prove it? The same way, the exact same way that I just told you to prove it for Tony. If we found the time associated with an x value of 20, then her height would still be positive. But then if we found the time associated with an x value of 23, her height would be negative. And so you would be well within your rights to conclude that at some point between traveling a distance of 20 and 23 feet, the height of the lawn dart was 0, and therefore it did hit inside of the circle. That would be a fine way to do it. Another fine way to do it would be to actually, use the quadratic formula to solve for the actual time when it hits the ground. So to do that, I would redefine my variables. The only one that has to change is C has to go up to 4. And B is now 25 sine 55. Redefine that as B. And now the real magic, I can just go right back up and get that expression. I don't have to type it again. It's already there. Grab it, use it, divide it by 2a. Blah. So there's the time for Sue's lawn dart to hit the ground. We shall store that as alpha s for Sue. Boink, we will go to our table, and we shall plug it in. Alpha s. Enter. All right, again, don't look at the blue. This is Frank's lawn dart. We don't care what Frank's lawn dart is doing at that time. We care about what Sue's is doing. We see we do have a height of 0. We see it's gone 20.822. So she's landing in the circle. Not by much, but by 80% of a foot she's in there. So like 10 inches in, but that's a win. She's in there. So that's the other, in my opinion, better way to prove that she has hit the target. So again, you could do either mathematical analysis. I don't care which. But whatever you do, I better see x values, times, and y values. So there. That's that problem. I guess I'll write my answer out formally. So I would say Sue's dart has a height y value of 0 when time equals something 1.452. At that time, x equals 20.833. Is that right? 20.822, damn it. Which falls between 20 and 23. So it does hit the target. Smiley face. That's a little bit angry. Oh, that's not angry. I forgot how to make angry. Satisfied. It's very satisfied with itself. All right, that's your entire homework problem. Notice I'm not showing work, and that's fine. The work, you get credit when you give me this time, and you get credit when you give me this distance. And I assume the work is happening behind the scenes, okay? So that's what I'm looking for. I do need the sentence. You guys can't just say, you know, yeah, she hits the target and expect to get an ounce of credit. Do your work. And write me those sentences that include those values, and that'll be all I need. All right, I hope this was helpful. It has been 52 minutes. I'm just going to let the clock run out. We'll stop it at exactly 53 minutes. All right, guys, bye.